So then I welcome everybody to this seminar of the Mathematics Division of Nanyang Technological University. Thanks to all for coming. Thanks also to those who are not physically in Singapore and nevertheless they are joining. So I'm very happy to see you. And well, our speaker today is Molei Tao. So Professor Tao is with Georgia Tech in the US. And well, from the point of view of his background, Professor Tao, he has degrees in physics and mathematics from Tsinghua, if I remember well. And then he went for a PhD in Caltech, where he got a PhD under the supervision of Umar Wadi, and then the late Jerry Marsden, who is one of the founding fathers of well, geometric mechanics and geometric approach to control. So Professor Tao, he's an expert in all these topics, and especially from the point of view of the numerical treatment of these things. So he has a very important contributions in well, symplectic and variational integrators with applications to ODEs, control, Hamiltonian dynamics. So that's the field where he has been working for a number of years. And well, more recently, these topics have become very important because actually they are the tool of choice for the development of convergence rates in very important contributions in the field of accelerated methods well, basically in optimization. And at the same time, this has a non-negligible interplay with machine learning. And well, Professor Tao, he has the perfect background to work on these things. So and since, as I said before, many of us are interested on these topics, well, we are very happy to have him here, and we look forward to his talk. So Molei, the floor is yours.
All right, thank you so much for this very generous introduction. I'm honored. So yeah, it's my great pleasure to be here and interact with the experts. So thank you very much for the opportunity, for the kind invitation. So what I'll talk about has a very long title, but what I'm trying to say is basically there's a very good collection of interactions between machine learning and dynamics. But because I guess here there are a lot of experts, so I can be a little more precise by saying that there are a lot of interesting topics, and what I will talk about is just a fraction of those research frontier problems, and those that I'll talk about are mainly going to be centered around mechanics. But I guess maybe it's helpful that I first describe a little bit about the big picture of some of the things that my group has been doing. So we are interested in understanding and exploring how dynamics can help design and analyze optimization, sampling, and deep learning algorithms. And in today's talk, I'll focus on the optimization part. I'll basically say something about how to do accelerated optimization in non-Euclidean spaces. Actually, in some of the non-Euclidean spaces. But also another thing that one can do is sort of like the reverse, excuse me, reverse direction, which is to use machine learning to actually solve scientific computing problems and even scientific problems. For that, I'll spend the second half of my talk on actually a very specific project in which we actually learn structured dynamics from data. And this very specific structure, which will be explained in details very soon, actually is very important because it enables us to obtain very accurate long-time prediction out of the dynamics that we actually learn from the data. And it is really this prediction, which is sort of utilizing the science that we extract from the data and makes new scientific prediction. And lastly, I'll briefly talk about some of the other aspects Namely, we will actually try to use dynamics to gain quantitative understanding of some of the deep learning practices. And in particular, we will see some of the interesting effects of large learning rate. Very roughly speaking, that will actually give you better test accuracy. But let me first focus on the first part, which is accelerated optimization. So given the smooth unconstrained optimization problem in vector space, everyone knows that gradient descent is a very robust and popular algorithm for solving this minimization problem, at least locally. But if you talk to a machine learning practitioner, sometimes when they say gradient descent, they actually thought about gradient descent with momentum, which is for good reason, because usually momentum-based method converges faster. And in fact, gradient descent with momentum is a family of methods. And one of them is called NAGC, which is the short for Nesterov accelerated gradient for convex functions. And the iteration rule is basically the one given here. You see there's a difference from the vanilla gradient descent because there's basically an auxiliary variable, y. Actually, I'll explain the role of this y later on. In fact, it's called NAGC, where C stands for convex for a reason, because if f is a convex function, bear in mind that f is the objective function here, then you can prove that vanilla gradient descent converges with a rate of 1/k. But if you do the same thing for NAGC, you actually get a faster convergence because the error decays like 1/k squared. So this is why people call this acceleration due to momentum. And of course, you may wonder what is exactly momentum here. So there are a lot of explanations. And I had a physics background, so I like the following explanation. More precisely, if you let the step size h go to 0 for gradient descent, then you see it's just the forward Euler discretization of a continuous dynamics. So it's a continuous meaning continuous in time, which is the well-known gradient flow dynamics. You can do the same thing to NAGC. You can let its step size eta go to 0. And in a famous paper by Su, Boyd, and Candace, they showed that this limit is actually a damped mechanical system. Okay, so x is the position variable, p is actually a momentum variable, and what is so therefore you can see this, because this p experiences not only the conservative forcing but also a time-dependent dissipation. This is naturally a mechanical system that is damped, and this p can be related to y. In fact, it's a rescaling of the adjacent y's. So it's basically this difference divided by h. So that's why this method is called acceleration by momentum. So all these are well understood, but what I want to talk about is what happens if your independent variable is not in a Euclidean space, but rather, for example, in a manifold, or a special case of manifolds, which is a Lie group. So how to make this to work? In the case of gradient descent, has actually been well studied. It's non-trivial because if you think about it, so if x is in a manifold, so this part is in a manifold, and this gradient is actually in a tangent. And then how do you do this linear combination? So this is actually not completely trivial, but those people and many more actually made substantial progress in this direction. But then what is new? Well, what is new here is we actually will try to add momentum on this manifold minimization problem. And if you think about it, the problem gets more challenging because, okay, so you may say, okay, so the x dot changes according to the tangent. But then what about so first of all, the momentum is not necessarily in a tangent space. So if you do it appropriately, it's actually in a cotangent space. But then how do you rewrite the right hand side here to make things actually work in a manifold setup? There are actually a lot of challenges, and therefore this adding momentum to gradient descent on manifold is sort of like an open problem for a very long time. So in part one of this talk, I'll present one solution which is ours, which is based on the following. So we will first obtain dynamics in continuous time that does some minimization on manifold, and then we will discretize the continuous time very carefully. We will discretize the time, and this way we will obtain numerical methods. And if you do that very carefully, you can actually get optimization methods that stay exactly on the manifold. So that's roughly speaking the roadmap. But of course I will be more precise. And in fact, my presentation in the first part will be based on a paper that is published in a premier machine learning conference, and that's joint work with my friend and collaborator Tomoki Osawa. So our approach is actually a variational approach, which is, in our opinion, very good for this kind of problem because in some sense it's intrinsic, so it's very friendly to non-Euclidean spaces. It also, it's basically a mechanical treatment which naturally introduces a notion of momentum. So of course, everything starts with mechanics, and mechanics started with Newton, at least the quantitative mechanics. And Newton said, well, the rate of change of momentum is given by the force. And of course, you can write down the definition of a momentum and then use Newton's equation to supplement it to get a system of ODEs. And of course, this is the usual mechanical system that we know. And then Lagrange came along. Lagrange said, that's right, but also you can alternatively consider a variational principle. So you can define an action functional, which is a function of trajectories, by integrating a quantity called Lagrangian, which is evaluated along the trajectory. And then if you look at the Euler-Lagrange equation associated with this variational principle, with a special choice of Lagrangian, which is kinetic energy minus the potential energy, then you can recover exactly Newton's equation. So these two are actually equivalent. So therefore, that's a new formulation of mechanics in some sense. But of course, you may wonder, how is this relevant to optimization? So far, there's really no relevance. And in fact, if you take a look at this Lagrangian, it's not explicitly dependent on time at all. And as a consequence of this symmetry, you actually have conservation law. The total energy of the system, which in this case is just the kinetic energy plus potential energy, is actually a conserved quantity. It's independent of time. So if you run this dynamics, what happens is that the kinetic energy is constantly exchanging with the potential energy. And by the way, here I use the potential energy as the function that I want to minimize. So you see that it's actually not going to minimize the potential energy because the value of the potential energy is actually going to be oscillatory. However, that's really because here this Lagrangian is not explicitly dependent on time. So if you introduce time dependence, then you actually break this time translational symmetry. And therefore, you don't have a conservation law anymore. And in fact, in a beautiful paper by Bibisono, Wilson, and Jordan, they adopted a very concrete treatment, which is to multiply the previous Lagrangian by a time-dependent factor. And then you can easily show that the corresponding Euler-Lagrange equation changed. It changed into actually a damped mechanical system where this gamma is basically a new term, and it's actually obtainable from this R in a very simple way. And if you don't recognize this as a damped mechanical system, you can still introduce momentum to be basically the same one as before, and then you see the forcing is basically the sum of two terms, and the first one is mu. It's a frictional force, and in fact, you can prove very easily by a Lyapunov argument that as time goes to infinity, the Q component of this dynamics actually converges to a local minimum of this potential energy F. That's why this dynamics is doing optimization, at least in continuous time. But then one can discretize the time. If one discretizes the time in some way, one can actually recover what I talked about earlier, this Nesterov accelerated gradient descent for convex functions. Okay, so therefore you have a duality between continuous dynamics and discrete algorithm. If you choose R differently, such that gamma is a constant, and then one discretization actually gives another member of the momentum family of gradient descent, known as NAG for strongly convex functions. If you discretize in a different way, then you can get another popular method known as heavy ball. And all these should be contrasted with gradient descent, which is a discretization of the gradient flow dynamics, but of course there's no momentum. Okay, so how is this again relevant to my story? So like I said, if Q actually lives on a manifold, then this equation definitely needs to be modified. And how to modify it is actually non-trivial. However, if you do not stare at this equation, but instead look at the deeper root, then you can see that you can naturally generalize this optimization dynamics to for example, Riemannian manifolds or special cases such as Lie groups. So that's the approach that I'll follow. Before I talk more about the details, let me still talk about, give a brief summary of what is a Lie group. I don't think the experts here need much explanation, but just in case. So a Lie group is a group that is also a smooth manifold. A good example is the special orthogonal group, which is a set of matrices that are orthogonal to each other and assuming a positive determinant. Why do I want to optimize over, for example, this group or this manifold?
Molei,
yes.
sorry to interrupt you. I don't know if the pages are, in what slide are you in now? Because
yeah, I think it freezes somehow.
It froze. Okay.
Yeah. So I don't know. Well, sometimes it gets solved by you stop sharing and then you come back and then it will start working again.
Okay. Yeah. Let me do that. Sorry.
No, but sometimes it happens. I think it's a bug.
Okay. Yeah. I'm sorry. Okay. So this is the slide that I'm on. So it says 2-1 on the top. Can you see it?
Well, he says, well, it didn't come back yet. So it didn't come back yet.
Let me try sharing my entire screen then. Maybe that helps. Okay. Can people see what I'm sharing?
Perfect. Now it's perfect.
Okay. So if I move to the next slide, can you see the change?
Yep. Now it's working. Now it's working.
Okay. Okay, thank you for letting me know. Okay, great. So so this is this SON group, and why do I want to minimize on this group? Here is a simple example. So suppose I want to do matrix diagonalization, which is of course important. I can formulate this as an optimization problem in which I try to pick an element of this G such that if I apply a similarity transformation based on this orthogonal matrix to a given matrix, then I want to have the result to have only non-zero elements along the diagonal. So that's why this is actually an optimization problem. At least that's one formulation. So so that's one reason why you want to do optimization on SON. But of course, you can do fancier stuff. So that's why we will study this optimization problem. But all I want to use is the gradient. So I don't want to use Hessian information. I don't want to use just the zeros order method, meaning I only query the value of f. But of course, then there's a problem, which is what do I mean by gradient? So if you think about it, this is actually not a completely trivial question, because for instance, if my group is SO2, so 2 by 2 orthogonal matrices, and if I pick my objective function to be just the determinant of this matrix, and then a person that is not careful would say, oh, then in order to compute the gradient, you just evaluate this determinant, and then you collect all the partial derivatives of this determinant, and then you form a matrix. That's going to be your gradient. But the truth is, because you are actually working with SO2, the determinant by definition is always going to be 1. So so the gradient should actually be 0 everywhere. So why is there a discrepancy? The reason is because SO2 is actually one-dimensional, a one-dimensional manifold, not 4. The A, B, C, and D are actually related to each other via this nonlinear constraint. So they are not independent variables anymore. So you cannot collect partial derivatives. So that's just the tip of the iceberg of why the field of manifold optimization is a profound field. Like I said, I'll only be focusing on a small sub-area of the field, which is how to add momentum. And like I said, variational principle is going to be very helpful. So let me remind you that in Euclidean space, I can simply use a Lagrangian defined like this to construct my variational principle. Now, if my Q, my position is no longer in a Euclidean space, but say inside a Riemannian manifold for now, then what I can do is I can actually replace the kinetic energy by a kinetic energy that is based on the Riemannian inner product of tangent vectors. And moreover, if my G is actually a Lie group, then I can even do more. So so of course, G is a function of time as it's a trajectory, and G dot is in the tangent space based at G. But what I can do is I can actually pull this tangent back to actually the tangent space at the identity element of the group, and this is known as the Lie algebra. And the way I can do it is I can actually take my G dot and multiply it by G inverse, for example, from the left, and then I get an element inside the Lie algebra. And then all I need is basically an isomorphism between this tangent space and its dual. And then I use a natural pairing to pair the dual with its an element in the tangent space, and then I can get my kinetic energy. So again, I think people here are experts, but if you haven't seen this before, I apologize because it's hard to explain in 3 minutes. But in that case, please trust me that you can actually write down the Euler-Lagrange equation for this variational principle. It'll look like this. So it's still a system of ODEs. G is sort of like the position variable, and it changes according to something like velocity, except that you actually have to left multiply C, which is in the Lie algebra, by G, and then this isomorphism actually sort of maps velocity to momentum, and then the momentum changes again according to a net force. It's just that here you have more terms. The first term is a frictional force. And this gamma, this coefficient gamma, is again given by this R coefficient that you can design. And if you choose R such that gamma is a constant, then you actually get a Lie group generalization of an AGSC. If you make it 3 over T, then you get a Lie group generalization of an AGC. The second term is interesting. The second term is actually a manifold generalization. It's something that you don't see in Euclidean space. It's roughly speaking like the Coriolis force, if you have some special case. But this is due to the curved geometry of the manifold. The third term is actually the proper way of taking the gradient, roughly speaking. But still, the set of equations is a little abstract, but we can work out, for example, concrete examples to gain more insights. So for instance, let's consider an easy problem, which is the leading eigenvalue problem. So you are given a matrix A, and I want to find the largest L eigenvalues of this matrix. This is the same as a minimization problem because I can simply add a negative sign in front of the matrix A. And then I can formulate my objective function f as follows. So basically, I look for special orthogonal matrices, a special orthogonal matrix that sort of diagonalizes this matrix A. And then I use a constant matrix to pick only the first L elements of the result, and I try to minimize the trace, which is the sum of their eigenvalues. So therefore, if I can find R that minimize this problem, I can basically find the corresponding eigenspaces. If I use this objective function and plug that into the Euler-Lagrange equation, I can get the system in yellow. And here, I don't even have to worry about the geometry anymore because here R and C are just n by n matrices. And so this dynamics is sort of like in the ambient space, except that if I start with consistent initial condition, meaning that if my initial R is special orthogonal and my initial C is actually in the Lie algebra, which is the set of skew symmetric matrices in this case, then no matter how long I evolve this dynamics, I'm actually staying in a submanifold in the ambient Euclidean space, which is actually the Lie group, the special orthogonal group for R, and the set of skew symmetric matrices of C. And moreover, this R actually converges to a local minimizer of the objective function. So that's the continuous picture. So far, everything's great. But of course, this is not a numerical algorithm. This is not an optimization algorithm. So we have to discretize it. And for simple illustration, I'll just use the constant time step for the discretization. Although the approach actually generalizes to variable time steps as well. So the way that I discretize this dynamics is basically based on operator splitting. So more precisely, I view the vector field as the sum of two vector fields. For the first vector field, you basically have a 0 in the R component, and then you copy everything in the C component. Oh, so I here replace this forcing term by a general forcing term, because this discretization is actually completely general, so it doesn't have to work only for the leading eigenvalue problem, which has this special forcing term. So that's my first vector field. My second vector field is sort of like the complement of the first, where you basically use 0 for C, and then you keep everything for the R component. And the reason that I'm splitting this way is because the associated flow of the first system and the second system are both explicitly known and exactly obtainable. So let's take a look at the first system. So here you see R is going to be a constant. So even though you have nonlinearity in the Cauchy equation in terms of R, because R is a constant, this G term is just a constant. So you really just have a linear equation to solve. So you can do that perfectly well. Similarly, you can do the same thing for the second equation. So Cauchy is going to be a constant, and therefore this R follows a linear equation. So you can actually obtain exact solution of this linear system. For the computational mathematicians, you may say, oh, that's true, but then you have to exponentiate a matrix. And if Cauchy is high dimensional, that's going to be expensive. So so in this case, you can actually reduce the computational overhead by something called Cayley transform, and still maintain actually the special orthogonal structure of R. And now what do I do? Okay, so suppose now I have the exact solution flow of system A and system B. Then I just do one H step. So H is the time of evolution. So I do H time evolution of B, and then I do H time evolution of A, and then I finish one step of the original system. So according to operator splitting, this is actually going to be a first order method. So it's actually convergent. Of course, if I want to do more steps, I just repeat this composition. And this is actually going to lead to a very good algorithm, because number one, that's going to be exactly on the Lie group. For example, you take a look at the flow of system A. R doesn't get changed, so R stays on the Lie group. Cauchy evolves according to this linear dynamics. Gamma is a scalar, so this part is not going to change the skew symmetry of Cauchy. And G is a forcing that you can prove to be always skew symmetric. For example, if you take a look at this special example, this square bracket is actually the matrix commutator. So that's going to be skew symmetric, and therefore Cauchy actually remains to be skew symmetric. And for the flow B, Cauchy doesn't change, so Cauchy remains to be skew symmetric. And R changes according to this exact dynamics. And because Cauchy is skew symmetric, the exponential of Cauchy is going to be special orthogonal. So if you multiply special orthogonal matrices together, you remain to be special orthogonal. The resulting method is also conformally symplectic. What that means is that, okay, so the original dynamics is actually not symplectic. It's dissipative, so it actually shrinks the phase space volume in a very specific way dictated by gamma. And the numerical method actually shrinks the phase space volume in exactly the same way. So there's not even any approximation. It's exactly the same way. So you inherit the conformal symplecticity of the original system. What I just showed is just the first order operator splitting scheme. So it's a first order method, but you can actually make it arbitrarily high order and keep it to be explicit, because there are higher order operator splitting and composition schemes available This is well understood, and because A and B are explicit, and so is their composition. And another interesting thing is the convergence of this algorithm is very interesting. So for popular eigenvalue methods in numerical linear algebra, oftentimes the largest eigenvalue or the spectral gap of the matrix A actually affects the convergence rate. And also for some other methods, the condition number also matters. Neither of these quantities directly affect the convergence speed of the algorithm that we have here. The argument is very simple. So if you take a matrix A, you add any constant scalar times identity matrix to this matrix A, then you shift all the eigenvalues. So you change the spectral gap, you change the condition number. But if you do that change to this dynamics, the scalar addition will actually disappear because you know you can easily see that due to the fact that R is special orthogonal. So the convergence rate doesn't directly depend on any of those quantities. So it's very peculiar. And finally, lastly, you have good generalization to machine learning problems where you have basically something called an online problem, meaning that you don't really have this matrix A accessible. So you only have noisy observations of this matrix A. And if you have such a situation, a lot of the numerical linear algebra problem, traditional linear algebra approaches may no longer work because, you know, for example, you may work very hard to construct eigenspaces, but then your A actually changes as you iterate, and then all your previous work gets actually messed up. But you can actually prove that if you follow this dynamics-based approach, noisy perturbations to A, for example, do not matter. Finally, I want to just emphasize that even though the red box, the yellow box has a special forcing term, this method actually works for general objective functions. And here is an interesting reference. This is actually a completely different problem in astrophysics. So here is a numerical experiment. So I'm dealing with a toy example. Basically, red is our new algorithm. Yellow is also another version of our new algorithm. So yellow is based on NAGC, red is based on NAGSC, and the other two lines are corresponding to existing good approaches. And the x-axis is the number of iterations, y-axis is basically how far away I'm from the maximum. So you can see a drastic increase of speed of convergence. But of course, this is just a toy example, but we can work with real examples as well. So here I'm performing some statistical analysis on the famous data set of MNIST. And this statistical test is actually just a generalized eigenvalue problem. And for this problem, we can still see that red is actually the fastest as well. Notice that the x-axis is actually in log scale. So even though red seems to be a little better than blue, which is actually the proper way of doing gradient descent, however, without momentum or manifold. So even though it seems to be close, they are actually very far apart. So let me summarize my first part. So by using a variational principle, we can get Lie NAG ODEs that do optimization in continuous time. We have to discretize the time very carefully, but that's possible. And then we get structure preserving integrators that actually correspond to optimization algorithms in discrete time. And these algorithms actually do gradient descent with momentum for Lie groups. Okay, so that's my first part. Should I move on to the second, or should I see if there is any question? Okay,
can I ask you a question?
Yeah, please.
In the previous graphs that you had in there, can you please remind us what the difference between the two accelerated methods were? So there was the C and the SC, I think. So, well, two slides.
Yeah.
Right, the one with the C and the SC, what was the difference between those two?
So, so C is for convex function, and it uses a gamma that is 3 over T. So okay. the friction coefficient actually vanishes in the long time limit.
Okay.
But SC is for strongly convex functions, and the friction coefficient is going to be a constant, and that constant is chosen according to the strong convexity coefficient of the potential.
I see.
So if you have strong convex functions, then SC is actually going to be the best. But if you only have convex functions, not strongly convex functions, then SC is actually not as good as C. So that's why both methods exist, and they just have their own application domains.
Okay, thank you.
Okay, great. I'll move on. Oh, is there a question in the chat?
No, I think it's fine. I think it's fine. Oh, no, okay. Sorry, yeah, there is a question from Ludmila, and she's asking why GHA has this drop in terms of iterations on the graph.
Oh, here. So if the question is about the non-monotonicity, that's because GHA is actually not a gradient flow. It's something else. Plus, here I actually hand-tuned the step size to be the one that gives me the fastest convergence. So this is actually large step size, which will make the numerical approximation not the same as any continuous dynamics. So I'm not sure if I'm answering the question.
Very good.
Okay, great. Thank you. All right, let me speed up a little bit. So second part is actually on a very specific work as well, under the umbrella of machine learning for sciences. So here we are trying to learn underlying dynamics that generate time series data. But I don't know the dynamics. So I want to learn this dynamics purely from data. And then I want to make predictions out of the dynamics that I learned. So I want to basically continue in time my time series. And this is an area that a lot of people work on. And one thing that our work focuses on is that we assume that the data is generated by mechanical systems. And let me explain a little more. So first of all, why do I want to learn dynamics of mechanical systems? That's because mechanical systems are everywhere. So here is one example in which I'm predicting the orbit of a planet. Well, I'm plotting the orbit of a planet precessing around a star. And of course, in practice, you don't see the continuous trajectory. So what observation gives you are discrete points, such as those in red. And maybe you want to actually make long-time predictions, such as the task of getting all those green dots. That sounds very like a task that is impossible, but bear in mind that this is a mechanical system. So you have actually prior knowledge about the system. But what exactly is the prior knowledge? Well, we know mechanical system conserves energy, conserves momentum, various sorts of momenta. But of course, if we dig deeper, there is this geometric quantity of symplecticity, which sort of gives rises to many of the conservation laws. So what I'm going to do is therefore to actually build symplecticity inside my learning model. And as a consequence, I will be able to get superior prediction accuracy, provable superior prediction accuracy. So the setup is very simple. I have training data which are time series. Here, I indicates discrete time, and J indicates which sequence that I'm looking at. So I can have multiple time series. And what I'm trying to do is to find a map phi. So I assume that there is an underlying map phi that basically evolves my discrete time. And the goal is to learn this evolution map phi. Of course, once we learn this, the task of prediction is trivial. I just keep on applying this phi. But bear in mind that I may actually want to apply it many, many times. So that sounds like a very easy, a natural task, very, very natural formulation. But in fact, traditional approaches are not necessarily based on this. In fact, most traditional approaches are based on differential equations, not maps. More precisely, it's often assumed that there is an underlying dynamics generated by some unknown function f, and then what you see are basically instances of this continuous dynamics. And the goal there is to learn this vector field f. But you see that learning f is not the same as learning phi. So f is in the tangent direction, phi is doing basically this jump. And in fact, because so if you try to learn phi, there are several sources of inaccuracy. Number one, you have to use some numerical differentiation. You have to use some way to approximate the time derivative from the discrete data. So that introduces error. Secondly, something dropped. Secondly, you have to approximate f. You have to approximate this function f, so you have function approximation error. And thirdly, suppose you have f, you have to numerically integrate this dynamics to get the future x. So you have three sources of error. Whereas if you use the above approach, you have function approximation error, so you have to approximate phi, but you don't have the first source or the third source of error. In addition, physics can be hardwired into this approach. So let me be a little more precise. So what do I mean by hardwiring the physics? What kind of physics? So what I'm talking about is actually symplecticity. So this phi in many situations has to be a symplectic map, which in plain language means that its Jacobian has to satisfy this quadratic nonlinear equation everywhere. Why do I have this requirement? Well, for example, if the latent dynamics is actually given by an ODE and it's a Hamiltonian system, then no matter what kind of Hamiltonian system it is, the evolution map is going to be symplectic. Okay, so that's why I actually want this constraint, and I want it to be a hard constraint. I don't want to have an approximation, an approximate satisfaction of this constraint, because then it's no longer mechanical. I want it to be exact. So previous approaches include using regularizers to sort of enforce it, but that's not what I want. So our goal is to find a map that reproduces the time series and also satisfying this constraint exactly. So that's not an easy task. So in order to ensure the exact satisfaction of symplecticity, we actually use an indirect representation of phi. So in fact, one can show it. Well, so there is a powerful tool called generating function from Hamilton-Jacobi theory, which is actually in one-to-one correspondence with symplectic map phi, as long as this phi is near identity. So meaning that you don't evolve the dynamics for too long. More precisely, so suppose this phi maps the current position and momentum to the future position and momentum. Then there is actually a corresponding generating function that actually depends on a mixture of present and the future. And this S actually going to satisfy this collection of PDEs. And therefore, what we do is we actually use, by the way, our method is called generating function neural network, because we actually use a neural network to parameterize this generating function, and then find the network that actually matches the training data. And then we don't have to worry about symplecticity. More precisely, okay, so I use a neural network parameterized S, and then I require this S to satisfy basically, this derivative evaluated at the current position and the future momentum is going to give me the current position, the current momentum. And also I require the second, I want to minimize the residual of the second equation. So I have the second term, and then I basically look for the neural network that minimizes this cost function. You can use any of your favorite neural network to approximate this as feed forward or residual network or fancier things. It's up to you. But the theory here has no restriction on what you need to use, as long as you have a universal function approximator. And then because we have a map approach, I forgot to say that because you look for S, and therefore symplecticity is automatically guaranteed. And because we use a map-based approach and we have exact symplecticity, we can use some KAM related technique which we invented to prove under reasonable assumptions a strong error bound, which is that, okay, so this part is basically the prediction, so the iterates of the learned dynamics, and this part is the truth generated by the latent dynamics, and their difference is actually going to be given by the right-hand side, where epsilon is basically your neural network function approximation error. So depending on what kind of neural network you use and how hard you train it, you can make this arbitrarily small. What we have here is actually the prediction time. So n is the number of steps, and here n can be actually arbitrarily large. And therefore, what we have here is basically saying that the prediction error is linearly growing with a long prediction time. And this should be contrasted with traditional approaches, which can actually have exponential growth of prediction time. And this is not even a loose estimate. This exponential growth of error can actually be obtained. So that's why when we test our method, for example, on simple tasks like predicting the orbit of a planet, our method basically has error that stays at the very bottom in comparison with popular approaches. So let me hurry up. But we don't have to always work with latent Hamiltonian ODEs. We can work with maps as well, because we don't really require any underlying continuous dynamics. So here we are trying to predict standard map, which is, first of all, not really a Hamiltonian ODE, but if you force it to be a Hamiltonian ODE, it's no longer a smooth Hamiltonian system. And also, it's actually producing chaotic dynamics. So what I'm trying to reproduce is the truth, which is the Poincare section of this dynamics. And here I'm plotting basically the Poincare section of several popular methods. This one is our approach. So you can see that our method is the one that captures most of at least the major stable islands, if you know what they are, what they mean. If you don't, I apologize. I don't have enough time. But basically, this is the best resemblance to the truth, and therefore, our method not only has good, strong accuracy. So in terms of trajectory, it also has good statistical properties as well. Yeah, so that's what I meant by this agreement. But let me summarize. So so we use a map-based approach, and And more precisely, we also use a generating function approach and use a neural network to parameterize this generating function. And then we get universal approximation as well as exact symplecticity. And because we have a map, we have a generating function, and we have exact symplecticity, we actually invented KM theory for generating functions. And using this analytic tool, we can prove superior long-time prediction accuracy. So I think, do I have one more minute? Yeah, okay. So
go ahead.
Okay, so the last part is no longer about mechanics, but I think it's something that we are pretty proud of. So we can use dynamics to understand important aspects of deep learning. So number one, we can show that if you use a large learning rate, you can actually escape from local minima, even if you use deterministic gradient descent. So there's no stochasticity anymore, but large learning rate can help you escape local minima. The reason is because if learning rate is large enough, the dynamics is actually going to be chaotic, and then you are actually no longer doing optimization. You're going to sample a statistical distribution, and this is how you can escape local minima in a very quantitative way. So more details can be found in this NeurIPS paper that we had. Another interesting aspect is that if you use a large learning rate, you can actually favor local minima that are flatter. You can actually converge to flat local minimum. And roughly speaking, the idea is that you utilize some symmetry of your problem and show that if you use a large learning rate, you actually have an implicit regularization effect of gradient descent, which sort of favors flatter minimum. And you can also find more details in this iClear paper. By the way, these are all major premier machine learning conferences. But that's all I wanted to say. This work will not be possible without my amazing collaborators, so let me thank them. And of course, thank you for your attention and feedback.
Thanks a lot, Molei. So are there any questions from the audience? If that's not the case, Molei, let me ask you something. Look, it's about part two. So in part two, basically you reduce the dynamics learning problem to basically learning using a neural network, the generating function, by encapsulating the problem in the context of Hamilton-Jacobi. So I have seen other papers that are not as nice as yours, where they learn directly the Hamiltonian function. So, but I think that at least the empirical results that you get are not comparable. I mean, this is much better. So, look, the question that I wanted to ask you is, well, the people around here and also the colleagues who are joining in the UK. So, look, what we are trying to do is to get basically what we're trying to do is basically what you are doing, but instead of using this static, this reduction of the dynamical problem to a static one by using the generating function or a Hamiltonian function, to go directly for the dynamical system itself. So to basically, well, you generate an autonomous dynamical system using a recurrent neural network, and then, well, you just try to impose on this recurrent neural network the necessary structures so that by construction, what you are going to obtain is going to have the, well, Hamiltonian conservative gradient group invariant structure that you know from first principles that your problem is going to have. So the problem in there is that, you see, we place ourselves in a discrete time setup because we want to put it in the computer. And then, of course, well, the systems that we are going to obtain, they are not anymore Hamiltonian. These are going to be, well, learning paradigm analogs of the integrators that our community has developed over the years, right? So what I wanted to have, or what we wanted to have, is your opinion on that approach. Do you know of anybody who is trying these things? Do you think it is reasonable? So having your thoughts on that would be very valuable.
Yeah, definitely. So I think you guys are doing very interesting things. So one thing that I can say is that, yeah, I think, I think this is an enterprise. This is a very active and emerging field that is exciting. So maybe the very first approach that you mentioned, learning the Hamiltonian is the one people commonly call HNN. Learning the Hamiltonian itself is not enough because if you first of all try to approximate the vector field from finite difference of the data, then the obtained vector field is not Hamiltonian because it's not infinitesimal. But still, you know, one can do things in an approximation. But then the prediction itself is also not Hamiltonian, not symplectic in the original paper of HN because they just integrated. But people can use symplectic integrators, and then later on, for example, there's this result called SRN. And by the way, they call it RNN because it's symplectic recurrent neural network, where they basically use a symplectic integrator so in the training process, they use a symplectic integrator to represent the dynamics generated by the Hamiltonian that they want to learn. So then they learn Hamiltonian. So therefore, there's no surprise. SRN is better than HNN in terms of accuracy. The original SRN uses the traditional splitting approach, which is just for separable Hamiltonian. But then I know people in 2021 that used my non-separable, so I had generic symplectic integrator for non-separable Hamiltonians. So they used my new integrator to improve SRN so that it works for non-separable Hamiltonians as well. And then there is SympNet. So SympNet is developed by somebody who's familiar with symplectic integrators, so Yifei Tang and his student in China, and they collaborated with Kaniakidis in Brown. So they had this very interesting result where they basically construct a different network architecture such that this network always represents symplectic maps. So the idea is based on, again, the splitting method for separable Hamiltonian. So you basically do like a gradient step that only updates part of the network. Well, so the network is, of course, a collection of many layers. So in one layer, you just do some of the components. So this way you can maintain symplecticity. And in some other layer, you do another gradient in some of the components, the complementary components. And then you can maintain symplecticity because this is essentially a symplectic integrator. So I'm not explaining this too well, but in a nutshell, they can represent symplectic maps exactly. But then the training of this network is not very easy, and it has to be very deep in order to have good approximation power. So in some sense, I mean, this is enforcing symplecticity in their network as well.
Because that's a natural question that one may pose when you look at this comparison between basically the performances of all these methods, because ultimately behind you have either a neural network or a deep neural network, and then ultimately there is a choice of architecture in there. So it is, I don't know how it is in your case, but usually it's difficult to know if the better performance comes from actually the method, or because of the neural network architecture that was chosen for each specific method, right? So it's difficult to make it comparable. So I don't know how you go about it, but that's the question that we regularly get.
Yeah, I agree. So that's why we were trying to have some theory as well. So we basically put everything about the neural network inside this epsilon.
Okay.
So all we need is a universal function approximation. But I agree with you. Unfortunately, so machine learning does require tuning, and how well one tunes can make a big difference. But by the way, in our case, we don't really need any fine tuning. So we can use any architecture. But of course, if you want to make it very deep, I recommend residual network at least. Yeah.
Excellent. Other questions?
I have a question. Hi, Molei. Just now you mentioned these people, they are using classical symplectic integrators, especially, I mean, you mentioned most of the cases they are using a separable Hamiltonian. Is it because in separable Hamiltonian, they can make it more explicit or more viewable? What do you think about this?
So a while ago, separable integrators, separable Hamiltonians admit good explicit symplectic integrators. So starting from 3 decades ago, people already knew how to make this to work very well. But non-separable integrators were commonly integrated using implicit methods if one still wants symplecticity. But this is so I had a fix to this issue about 5 years ago. So now for non-separable mechanical systems, you can also do explicit symplectic integration as well. So the SRN authors are very good, but they were not experts in geometric integration, so they used the traditional separable integrators in their work. But then people realized that there are recent updates, and then people started to improve SRN by generalizing it to non-separable problems as well. So
SampNet is the one that uses non-separable Hamiltonian, and which is explicit symplectic integrators, right?
No. So SimpNet is not based on integration. It's based on representing symplectic maps. This is not based on integration. I'm not sure if I'm answering your question.
Yeah, thank you.
Yeah, so if you want references, you can send me emails. But also our paper has a review of some of the things that I talked about. But I know there are. I mean, it's published last year, and I know there are many recent progress. So yeah. What I'm saying may not be complete or even up to date.
Excellent. Any other questions? Very good. So then I'm going to thank our speaker today for staying up late and well, for taking time away from your family, because I know that you have small kids. So and also to thank our colleagues and friends from the UK, because I don't know what you are doing there. It's the middle of the night. So thanks for being there. And yeah, so I'm going to close the session. And thank you all, and then see you next time.
Thank you all for coming.